I've got the formula for W. So now we can find the formula for eta. So let's see here. Eta of, how's it go? X plus jy, I suppose, right? Should be psi inverse W of psi of that. So, now that's X plus Y, right? X minus Y, that's psi. So if we plug in, this is actually W of ST, right? This is W of ST, so basically like S equal to X plus Y, T equal to X minus Y. So I get psi inverse of C1 e to the twice X, let's say S, but here's S is X plus Y. And then C2, easy enough. And I have to take psi inverse of that. Now what was the formula for psi inverse? Psi inverse of X comma Y, I believe, is X plus Y over 2 plus J times X minus Y over 2. That checks because if you plug in 1, 1, you get psi of 1, 1 is 1. Psi inverse of 1, 1 is 1, and you get psi of 1 minus 1 is 1 minus minus 1, which is 2 over 2, which is J, and that's 0. So, yeah. There it is. So then we got to do psi inverse of this thing. So we're supposed to add, and divide by 2. And plus J. Let's see one. Oh. So let's see here. And that is what I have on 87, isn't it? We did it the same way, at least. So it's either right in both places or wrong in both places. Now, I would say that that's okay. I mean, fine. That's the method. That just illustrates the method. Of course, this problem, there's like what's an easier way to solve this problem? We have a factored form at the start, right? When there's just one root, there's no issue of differences being 0. I mean, it goes back to one of our fundamental lemmas.
Oh, yeah, the flat 13? No.
Something like that. This is maybe before that. Eta equals to, speaking of eta of z, equal to, some constant times e to the 1 plus j. Z. I mean, that's from this.
Yeah, so you get, okay.
And this can be rewritten as C1 e to the 2 times x plus y. Because these, it's 1 plus j, that's the thing I keep forgetting. C1 plus j. There's divided by 2, we gotta find. Plus C2 times 1 minus j over 2. Funny. I claim that this solution and that solution are actually equivalent. a short calculation. I don't think that, I mean, I'm not interested in doing that calculation today, I'll just say that, okay? And here's another example where I take a H4 ODE. Of course, H4 is isomorphic to R2 cross C, according to that isomorphism. And so I take, I take this quadratic, second order AODE and H4, and I convert it to a pair of, well, I guess 3, right? I get 2 real, the W1, the W2, those are real, and then W3 is complex. And then I say, okay, so that solution then is what I write there on equation 91. And then, then I say, and I am not going to write down how to get back, but it's clear. I mean, it's you start to see why I don't like this method. Yeah, I can go back, but it does tend to produce solutions which are, I would say, inelegant. But anyway, there it is. And I have checked that that solution is in fact, well, maybe I haven't said. I said it may be interesting to relate to that solution to the natural one that is obtained by, B1 cosine j zeta plus b2 sine j zeta. So, because remember here, eta prime plus j squared eta, it does have the natural solutions of cosine j zeta and sine j zeta, because if you differentiate cosine j zeta, you get minus j sine j zeta, and then differentiate again, you get j squared minus j squared cosine j zeta. So the usual, like we learned in Daniel's paper with the Pythagorean theorem, that the usual laws of calculus apply to sine cosine. So like it's just basic calculus that cosine j zeta and sine j zeta are going to solve that eta prime prime plus j squared eta equal to 0 problem. And it would take me some time to understand exactly how this isomorphism solution relates to this natural solution on H4. Anyway, I hope that's enough that you see that it's a method that we can use. There's a clear path if you have an isomorphic algebra to like break it down into bracket pieces. That said, I'm so happy that we're now to section 5.3 because this is by far my favorite. Was there a message or something?
Extra to give.
Now, I think Nathan's algebra paper is actually very helpful here because he really introduces us to the kind of algebra that quickly removes doubts about the plausibility of some of these calculations we're about to do. Because basically he gives us a roadmap to how to create algebras that satisfy relations that we want. And the roadmap is pretty simple. It's just take polynomials with coefficients in the algebra that you got, and then that set of polynomials is infinite dimensional, right? But what you then can do is take the quotient by the relation that you're interested in. And in so doing, you descend from this infinite dimensional polynomial space to a finite dimensional quotient space, finite dimensional of the algebra. And then that finite dimensional quotient space is exactly the thing you're trying to create because it has elements in it which satisfy the relation that you're after, and it's not infinite dimensional anymore because dividing by, or rather forming the quotient by an ideal, it allows you to collapse polynomials down to basically something that's related to the size of the ideal you're quotienting by. Now, so he used this technology to derive his isomorphisms of like n complicated numbers and other things in that algebra paper. The basic thing that it always falls back to is if you have, so an ideal, talk about ideals of a ring. What's an ideal?
Like nice properties?
No, an ideal is a specific subset of a ring.
Okay.
An ideal of a ring is like, okay, you could, on one hand you'd like to say, well, they're normal subrings. If you're fond of group theory speak. Or maybe we should, instead of talking about normal subgroups of a group, we should talk about ideal subgroups. Because it's, well, I don't know, maybe it's a little bit too much. But basically it's, an ideal is a subset of a ring which allows us to make the factor ring itself a ring with respect to the natural operations. But an ideal, let's see here, maybe best to illustrate by example. 3z is an ideal of the integers y. Basically this, if you take s, well, let x be in 3z, right? And x be an element of the integers. Oh, sorry. N be an element of the integers. Then nx, right, is equal to what? It's equal to n times 3j for some j, right? By definition of 3z, right? And of course that's equal to 3 times nj. And so that's what? That's an element of 3z again, right? So an ideal is a subset that when you multiply it by the ring, anything in the ring, it ends back in that set again. That's one thing the ideal is. I think it also has to be a additive subgroup. I could be wrong about that. Let me think about that. No, that's wrong.
So an ideal is a ring, is a subgroup of a ring that's also a ring?
Is it though?
That's my question. Yeah, I'm sorry. Let me double check on
not butchering the definition of an ideal here for a second. Actually, let me fix the camcorder for a second.